All right, John, I'm ready. You can lower me down. Now, you may wonder what this strange contraption is. Believe it or not, I'm about to be fully supported, in fact, there it goes, from a bridge made of spaghetti. That's right, pasta. And Kathy French, a professor of civil engineering at the University of Minnesota, is here to tell us how this underslung bridge built entirely of spaghetti and glue could possibly support my weight. Welcome to the show, Kathy.
Hi, David.
It's doing all right, isn't it?
It's doing great. Actually, you're illustrating an important point right now, and that's that bridges can weigh a lot less than the weights that they're designed to carry.
Okay, so how much does this spaghetti bridge weigh?
This one only weighs 1.5 pounds, about 8 servings of linguine.
So where'd this bridge come from?
This one comes from British Columbia, and a similar bridge was built there for an annual spaghetti bridge building competition, and if you would believe it, that one carried up to 400 pounds of weight.
No kidding. So this bridge right now, as we can see from the scale, is supporting, what, about 100 times its own weight, and it's working only at about 1/3 of its capacity at this point.
That's right.
It's phenomenal. This whole thing started, Kathy, because we got this letter from Emily Gisselberg from Tigard, Oregon, and she wanted to know, how do different bridge designs work? She didn't say anything about spaghetti.
We're going to answer Emily's question today by building some bridges and also destroying some in the process. So why don't you hop on down and let's take a look at some bridges.
Okay. Look at all the different bridge models you've got.
Well, David, it might look like there's a wide variety of bridges, but actually there's 3 basic concepts, and those are the beam, the arch, and the suspension bridge.
Do each of these designs support weight in a different way?
Yes, they do. What I'd like to do is to test your skills as a bridge engineer and have you build a bridge. I'm going to give you 3 pieces of cardboard to make your bridge, and I'd like you to span it between these 2 supports.
Okay, well, the cardboard feels pretty stiff, so let's just try one straight away like that.
Okay, let's test it out and load it with a truck.
Okay, here goes. I don't think
It didn't work quite so
ready
well.
for the big time in bridge engineering.
There's a few things that we could do to make it work. One would be to put a support in the middle. And
that would mess up boat traffic, though, wouldn't it, down below?
That's right. Another way would be just to use the material and change the shape. So this is, again, the 3 sheets of cardboard. But what I've done is taken that middle sheet of cardboard and made a triangular shape out of it. This is called a truss-type bridge.
So you think this is going to be stronger, huh? Wow, look at that. It's a lot stronger.
That's right. By changing the shape into this truss form, what we have is a section that's much stronger and also much stiffer. It sags less.
You know, I've actually seen this kind of zigzag accordion design in metal bridges before. Can you do a truss out of something other than metal?
You can. You might see a wood bridge made into a truss shape. And your question about materials is an interesting point. Years ago, in ancient times, the Romans built bridges. The only material that they had available at that time were stones. So they had to come up with a shape where stones would work. Right. The shape that they came up with is an arch. And I'd like to show you an example of that type of bridge.
Okay.
Why don't you hop up on there and we'll see how it works.
Of course. Hop up. What's holding the individual stones together? Mortar?
There's nothing between the stones.
There's nothing holding them together. I get it. So why does it support my weight?
The way that it works is your weight is being put on the bridge, and that weight is pushing all these stones or blocks together. The only way that stones can support weight is if they push against each other.
So the symmetry here is important. This little wedge rock in the middle pushes in both directions?
That's right, and pushes your weight right on down to the floor.
So what happens if one of the stones gets displaced slightly?
Let's see what happens.
Wait. Let me get off the bridge first.
All right. This top stone here is called the keystone, and the reason it's called it, it's the last stone that's put into place when the arch is being constructed. Let's see what happens when we pull it out.
Remove this one, huh? Uh-oh, here goes. The bridge falls down.
That's right. That would happen no matter which stone you took out of the bridge. You get a collapse.
Nothing but bridge debris left, huh?
That's right.
Kathy, what's all this extra debris over here on the side?
This is actually from another type of stress that bridges are subjected to, and that's environmental stress. You can see parts of the bridge that were subjected to corrosion. In the northern states, we put salts on the roadway to keep ice off so cars won't slide.
So the rain, the snow, the wind, that's one thing, but
right.
Salt is quite another.
Right. And I'd like to show you a video. This is a Mendota Bridge, which links Minneapolis with St. Paul across the Minnesota River. When it was built in the 1920s, it was the largest continuous concrete arch bridge in the world. And you can see part of the bridge is removed. The roadway surface is already removed. It's under rehabilitation because of corrosion problems. Here you can see them removing the roadway. That's because the salts are directly applied to the roadway, and so that's what will deteriorate first. The arches themselves are in pretty good shape. Here you can see they're pouring concrete for the new deck that's being put on, the new roadway surface.
Kathy, why did they choose to use an arch design in that particular bridge?
Because there they had a relatively narrow river crossing and a wide river valley where they could place a lot of piers. If you had a wide expanse of water that you might want to traverse with a bridge, you might want to use less piers, and you might want to go with something like a suspension bridge instead.
So how does a suspension bridge work?
Let's go find out. You are walking out on a working suspension bridge.
Oh, so far I'm walking.
So the difference between this and a real bridge is that rather than the cables being anchored into the ground, we have a group of bridge wranglers supporting those cables.
Welcome, bridge wranglers. Glad that you're there. So what holds the whole thing up?
The way that it works is cables only work when they're being pulled. They don't work at all when you push on them. And so what's happening is your weight and the weight of the bridge is pulling down on these cables. These cables in turn then are pulling down on the main suspension cable, which is pulling on this pier or support, and it's also pushing down with your weight on the support. The wranglers there are holding the cable back.
And doing a good job of it, too. So what happens if one of those cables were to get damaged and loosen up or something?
Let's see what happens. You heard him, wranglers.
The bridge falls down.
That's right. It collapses, and when the wranglers let go, what happened is the tower collapsed or was pulled in. That's because your weight's pulling down on the towers, so you need them to anchor the cables back.
A lot of pulling pressure here, isn't there?
That's right. It only works when the cables are being pulled upon.
Okay, so the bridge is supporting or suspending the entire road surface. It's also suspending all the vehicles that are driving over that road surface. How do they do this with really long suspension bridges like, say, the Golden Gate in San Francisco?
Well, let's take a look at a little model. This is our model of a suspension bridge, and the reason that it can span large gaps of water is because it's made of a relatively lightweight deck or roadway supported by cables, and that way you can span large distances between the piers. Sometimes, though, you can make the deck a little bit too lightweight or flexible, and I'd like to show you some video where that's just the case. This is the Tacoma Narrows Bridge in the state of Washington, and this bridge was built with a very lightweight deck, and they found that out very soon after they constructed it because it started to vibrate under very light winds. You can see on a day in 1940, under just about 40 miles per hour of wind loading, the bridge started to sway and twist and got itself in a mode where it just ripped itself apart.
That is just completely twisting.
It's amazing.
And then it totally rips itself apart. Now, you don't see that happen every day, obviously.
No, hopefully not.
Somebody is figuring this out, where they can build a light road surface but still have it be strong. How do they do that?
Right. What the key is you want it to be lightweight, but you want it to be stiff so that it won't twist or deflect a lot. And so what they've done is you can see in this particular bridge is showing one way of doing it, if you recognize it.
This is the truss from what we looked at earlier.
That's right. Here it also stiffens things up, and it has the advantage, too, of these gaps allow the wind to flow through. Nowadays, too, that if they know that a bridge would be in a situation where it might have trouble with wind, they build a model and they test it in a wind tunnel first.
Ah, that would have been smart in the 40s, huh?
That's right.
Kathy, thanks so much for explaining bridges. I have a whole new insight now when I cross a bridge.
You're welcome.
What do you say we go over and try this pasta bridge one more time?
Sounds good.
I figure if it breaks, we'll always have spaghetti for dinner,
Okay.
huh?